Hello, my name is Jorge Garcilaso, and this video will serve as an introduction to the topic of the root locus method in control systems and how to utilize this method to aid in control solutions. In simple terms, the root locus is a visual tool for us to achieve stability in a system by changing the value of the parameter k. The root locus is a graph that allows us to see how the poles of the closed loop system change as we vary the value of k. For us to better understand the root locus method, let's start with an example of a system that is governed by this transfer function. As you can see, this example is fairly simple and straightforward. Looking at the function, we can see a 0 at -1 and two poles at both +1 and -2. Because we have two poles and one 0, there is a second 0 at infinity. It is common to encounter variable parameters such as k in many control system problems. Because this variable parameter is unknown and its value affects the poles of the system, a recurring question is what value of k should be chosen to meet the system requirements, and what is the effect of a variation of k on my control system. Choosing different values for k changes the positions of the poles in the plane, and this is exactly what the root locus method does. It is a graph of the variations of k in the S-plane. Now that we know where the poles and zeros stand in the graph, let us draw this in the S-plane. The S-plane is drawn with imaginary components in the vertical axis and real components in the horizontal axis. Poles found in the negative plane of the real axis indicate that the signal of the system decays, and the further away from the origin, the faster it decays. On the other hand, positive values behave in the same manner, but represent an exponential growth of the signal. The imaginary values represent the oscillating behavior of the signal. These are always found in pairs, and their distance between them represents the number of oscillations found in the signal. The further from the real axis these values are, the faster the frequency of oscillations. The system's poles are directly related to the stability of a system, and their position in the root locus S-plane helps you determine its stability and whether the response will be oscillatory, exponential, and its frequency. This is why the root locus method is really important. Let's refer back to our example and how our control system initially behaves. As we can see, there is a pole in +1, and therefore the system is unstable. However, as we increase the value of k, we can see that our poles tend to move towards -1 and infinity. The question then for our system is to know at which value does our pole transition from positive to negative. In other words, at which value of k do we get a stable response? For that, let's refer back to the original equation of the system, where 1 plus k times gh equals 0. We can solve for k in this equation, and we can get that the value of k can be found by 1 over gh. We also know by looking at the graph that the output signal becomes stable when s equals exactly 0. So if we substitute s by 0 in the transfer function and plug that into the equation of k, we should get the value of k. Once we solve for k, we arrive at the value of 2, and this means that the system becomes stable after the value of k reaches 2 or above. This was all thanks to the visual aid of the root locus graph and method. Now, let's dive deeper into the graph, as there is also more information that can be useful for problem-solving control systems. Lines of constant damping ratio can be drawn on the root locus graph, and these lines move out of the origin at a value of cosine of phi. This is important because in many problems, engineers are required to come up with a solution under a certain damping ratio. This means that the value of k must be inside the cone done in the graph. Sometimes you are required to time to half, which means the mode must decay to half its value under a certain time. Since this signal decays faster depending on the distance inside the root locus graph, all the poles must be found on the left of a certain line. Another requirement is the natural frequency. For example, you are given the requirement that the mode must be slower than 1 radian per second, and therefore your poles must fall inside a certain section of the graph. You could be asked to meet a combination of these requirements. The root locus method allows you to visualize these things and adjust the value of k accordingly, and this is why it's important to understand and know the root locus method.